So we've been we've been using this, and we've been using this kind of implicitly. We've been dealing with this change of variables when we do a polar coordinate transformation, or the last two things that we did, the cylindrical and spherical coordinate transformations. So we have been using this idea already. And so now, the way they presented it, they didn't use the Jacobian back in those sections. They just said, well, if you're going to go into polar coordinates, there needs to be a change in the area. And so they need to compensate for that change in the area. And so that's, you know, if you look at the book, the information that they have in the book talks about how the R comes from geometry. And we kind of took it from this. So we've been doing the Jacobian more explicitly in our class than the book was presenting in the book. So the neat thing about this is that we're not just restricted to polar coordinates, or in 3 dimensions, we're not just restricted to spherical and cylindrical coordinates. We can handle a lot of other transformations. Now, a lot of those other transformations might be difficult, and in the problems that you'll get, you're actually going to get these transformations given to you, much like you're given the polar and cylindrical coordinates. But this is a general setup for a generic change of variables. So think about it as a U substitution, or think about it as a trig substitution, even better. So if we can make an analog to trig substitution, from Calc 2, we would have some function here of x dx, and then we would make a substitution where we say x is equal to maybe like a sine theta or something. And so in this substitution, we would write f of a sine theta. Wherever we see an x, we would replace it with a sine theta. And the trig substitution is nice. I mean, it's set up for you to be able to use the trig identities and stuff. But the other big thing is that when you change your variables, you have to compensate for the change in the function. The differential dx needs to get changed. And so we find a differential here. And that's what we replace the dx by. So that now it's just a function of theta. So that's exactly what's happening here, except this, what we call our differential, is really the one-dimensional Jacobian back in the trig sub days. So it's all there. We have done it before. Now we're just going to do it for more complicated scenarios. Okay? I don't know if anybody's taken a look at 1510, but you used to have 6 problems there, and I cut out 2 of them. And so the 2 problems that I cut out had to do with geometry, and I figured you probably didn't need to deal with geometry. So, so now you just have 2 problems where you actually compute the Jacobian. I think you could do that. And then you have 2 problems where an integral is involved. The last problem, though, we'll do the last problem. The last problem has this idea of what the regions would look like. So I kind of wanted to not talk about the geometry of it, but I kind of feel like I'm compelled to talk a little bit about it. So let's talk a little bit about the geometry, and without needing to know any of this. So what we have is a region on the xy plane that may be complicated. And then the transformation that we're talking about is a transformation to another plane, whether it be r theta, and we saw the simple drawing with r and theta, but we can generalize this to two other variables, and the usual variables that they use are u's and v's, where hopefully you have a nicer, simpler looking region that we'll call d star. And your transformation is usually described as x is equal to some function of u and v, and y is equal to some other function, g. I think this is g and h. Doesn't matter. Those are just names. And what we have here, it's called a pullback. It's a pullback function because you're inputting your u and v into the function to get an x and a y. So really the arrow for this goes from the u, v as a domain, and then the x, y as your output, your range. So of course we want to make sure that this is differentiable because we're going to need to take the Jacobian. Jacobian has derivatives involved, and so we want to be able to take derivatives of those things. And so the idea is that we have a double integral here over d, and we're hoping that when we go back and eventually make the substitution, we will have a d star that would be a nicer region. We can integrate easily, and hopefully along the way our integrand gets simplified by putting in these values for x and for y. And then now our dA, which used to be dx dy, is going to change into du dv, but before we do that, we have to make sure that we include our differential, or in this case our Jacobian. And then finally we get the du dv business in there. Okay. So I was trying to do this transformation using a graphing calculator program just to see how it would look like, and I was messing around with it, and I don't know if I've completely figured it out. So let me try to do this in a couple of minutes, and if it doesn't work out, then it's not going to work out. I think the transformation that we can do is, let's do the polar coordinate transformation first. And for the polar coordinate transformation, you have r cosine theta, but it still really involves x and y, so I'm going to put x times cosine of y. That's like r cosine theta, x sine of y. And if you look at the graph here on the right side, it looks like my graph paper here became a polar coordinate graph paper on the other side. And so what would be interesting to find out is, well, this line also, there's something interesting about this line. This is the purple line. Let me change that line. So if I have a line, okay, let's see. X is the R value, right? You have to pretend X is R, and then X prime is like our X. That's kind of confusing. But anyways, this line, if you look at what's happening with the line on the left side, that's what's happening on the right side. Okay? So now let's have another graph going on. Let's get y equals b into this picture. Y is like the theta. And if you look at that red line, as b increases or decreases, as b moves along, you're going to get the line segments from the origin, describes radial distance. So if your r is, say, between 0 it's x, right? If your x or your r is between 0 and 1, and then your theta is between 0 and pi over 2, what do you think you'll get? X is r, y is theta. What are you going to get? Yeah?
Like
a quarter of a circle. So on the left side of the graph would be my r theta limits, and then on the right side of the graph is how we would see it. So let's change r to go from 1 to 3 or something like that. So that's how it'll change. In fact, we can change this into A and B. Just for fun. So you can see how things change like that. Okay? Is that pretty cool? Yeah, that's cool. All right. So now, let's take a look at an example. I didn't come up with an example. Let's just do your homework. You only have 4 problems. So I was interested in doing the last one. Ooh, the last one looks like there's a graph. Let's see if we can dig down and get a good understanding of this. So use a given transformation to evaluate the integral. So evaluating this integral isn't so bad, but it's trying to evaluate this limit over here, or this is bounded by the curves. That one looks a little bit more difficult. So let's see if we can find the region. So they give us a substitution here, right? And this, so trying to find this region, I think if I solve for y, for all of them, I might get some idea of how this thing might look like. I still might want to graph it. So maybe this is something that your graphing calculator should be able to handle after you've been able to solve for y. Let's see if I can graph it using my graphing calculator. So I have xy equals 2, xy equals 7. So they look like that so far. And then let's take a look at xy squared equals 2 squared, what? Equals 2, and then xy squared equals 7. So it's kind of confusing when you see all those graphs at the same time, but what you have to do is try to imagine where the intersections are going to be and where the region might end up looking like, or what the region might end up looking like. So if I extend this out and I kind of see a bunch of intersections, so I have this, and then I'll change to the blue. Whoops. Maybe I'll shrink this down a little bit. And then they'll intersect here somewhere, and then the red graph. Ooh, that's confusing. Anyways. I don't know if you can see the region, but looks like it might be from here to here, and then comes back up to here, and then over here. I don't know if I just messed that up for you, but that's where the region is. It has all four of those functions put together. Now, the tricky part is that this is what's happening on the xy space. And what you want to do is you want to go to the uv space and figure out what happens to this transformation when you let u equal to x times y. Oh, that's u equals xy. What? Yeah. So I think if you have this information, you're kind of given the u values, 2 to 7, and then you're given the v values, 2 to 7 as well. Okay. So, but this is still a little tricky because we still want to be able to solve for, we still want the x as a function of u and v. And so So first of all, let's acknowledge that we got d star. That's going to be our new set of limits of integration. We're going to go from 2 to 7 and 2 to 7. So that was nice. But now the tricky part is to find a Jacobian. Remember that the function has to be written as x as a function of u and v. Y. Wait, let me see. X and y in terms of u and v. And what was the idea?
We can isolate y from x, right?
On the first one?
The v is equal to xy squared and v is equal to xy. So xy equals u times y is v. So v
Equals u times y.
No, wait. V equals
What?
u equals xy, right?
U equals xy.
xy times y or uy. Right?
Yeah. So y equals uv or v over u? That make sense? All right. So if we have y is equal to v over u, then we could probably, what else can we do? Back into maybe the one with the x. Not that, I don't think it matters. So u is equal to x times v over u. And so I would solve for x here. X is equal to reciprocal u squared over v. So that's our pullback function. Yeah. Because we want to write a set of equations where we have x equals something and y equals something with u's and v's in it, so that we can do a Jacobian. And so any way you can, you solve for x and y in terms of u's and v's. So I think here we got u squared over v and v over u. Okay. All right, so let's find the Jacobian. The Jacobian is going to be partial x and y over partial u and v. And that's, we need derivatives of the first one, derivative of x with respect to u. This is going to be 2u over v. The derivative of this over v, that's negative u squared over v squared, v to the negative 1. Yeah. So the derivative of this one is going to be negative v over u squared And then the derivative of this one with respect to v is just 1 over u. Hope I did my derivatives correctly. One of the famous derivatives that you kind of need to be able to do quickly is like 1 over u, or 1 over x. It's x to the negative 1 power, so the derivative is negative 1, x to the negative 2. So we did that in a couple of places here. Not square root. Oh, the derivative of x to the 1/2. That's another good one to try to remember. So anyways, the determinant is going to be, let me write it out and then I'll do the canceling after. So it's going to be these two, the diagonals minus a couple of negatives would cancel. All right, let's take our canceling pen. It's gone. One of them is gone. So I have a v in the denominator and then another v. What is it?
2 over v minus 1 over v, or 1 over v.
Just 1 over v. That's nice. Okay. So that's your differential. That's your Jacobian that goes with a change. Let's take a look at our integral again. Our integral is integral of 6y squared dA over that region that was hard to identify. So integral over a region 6y squared dA. Now, given what we have, we're going to integrate this with du and dv. Our 6 or y is equal to v over u squared. And then that's it. There's no x's, so we don't have to replace the x. And our dA is going to become the Jacobian, 1 over v. And then now we do a du dv. And the du dv doesn't really matter which way we do it. We just have to know the limits. The limits turn out to be 2 to 7 for both of them, right? With constant limits, 2 to 7, 2 to 7. So this is a manageable integral now. Okay, in fact, since we have constant limits and then these are factors that you can take out, you can take the 6 all the way out, and then you can decide to integrate with respect to v first, and the v, well, one of the v's on top would cancel with the bottom, so that would just be 1v. And then since this is something that you can separate, you should be able to do those two integrals quite easily. Okay, any questions? All right, I want to try one more thing with this graphing calculator. And what was our transformation again? Our transformation was, Yeah. Did you have a question? Oh, the question was what was u and what was v, or what was x and what was y. So x is u squared over v. So I'm going to, whoops. X u squared over v, so I'm going to use x squared over y. And then what was y equal to? V over u, which will be y over x. There's weird stuff happening. But if I take out the axes, this over here would be the region that we were talking about. So if I draw those graphs, sorry, disappeared. If I draw those graphs, x, y is equal to 2. There's one of the graphs that's touching one of the sides. xy equals 7. There's another graph touching this side. And then, what is it, xy squared or something? That would be hard to see. Let's make it black. It's right along the bottom edge. And then the last one is 7. Uh-oh, that one's not involved. Should be over here. Well, something happened. It's supposed to be down here. I don't know what happened. Well, let's just pretend it's touching. All right. Are we okay with this? Aside from my graph not touching. Right? Why did the last one not touch? I don't know. Oh well, we'll have to figure it out later. How you guys doing with the homework and this class and things going okay? And you guys can do cylindrical and spherical coordinates and stuff? All right. Let's see. Let's take a quiz. You guys have to take out a piece of paper for this quiz. I didn't. What?
Where's the quiz
The worst quiz yet. Worst quiz ever. Is it the worst quiz ever? What? It doesn't matter. Worst quiz ever? Oh, I should stop this now.